In today's video, I'm going to be talking to you about the Courant number. A good understanding of the Courant number is essential for anyone who's carrying out a transient CFD analysis. What I'm going to be showing you today is a derivation of a generalized form of the Courant number that can be applied for arbitrarily complex 3D cells. So cells that are skewed, maybe polyhedral cells, hexahedra. The derivation of the Courant number I'm going to show you today is valid for all of these cells and is used by the majority of CFD codes. To finish off the talk, I'm also going to be looking at a variety of misconceptions around the Courant number, which you may not have come across in your own studies. And finally, I'm also going to be looking at adjustable time stepping and how the CFD code actually goes about adjusting the time step based on the Courant number. I know you're going to find this talk extremely useful. Here we go. So before I jump into the talk today, what I want to do is just briefly mention some of the nomenclature that I'll be using in today's talk, because it might clear up a few things for some of you listening. The first thing to note is that Courant, Friedrichs and Lewy published their original paper in 1928. And as a result of this, you'll sometimes see the Courant number referred to as the Courant Friedrichs Lewy stability criteria, or the CFL number for short. And this is just an alternative choice of notation to the Courant number. They all mean the same thing. And in this talk, I'm going to be using the Courant number to denote the quantity that we're looking at, as this tends to be more common in CFD codes and in user guides, and most people tend to be more used to it. So if you hear people refer about the CFL criteria or the CFL number, it refers to the same thing, but I'm just going to refer to it as the Courant number today. And for those of you who are interested, the original paper in 1928, I've put a link to that paper in the description below, so you can have a read of it and have a look if you're interested. Now, moving on to look at 1D cells, which you're probably all familiar with by now, we're going to motivate the talk and start the analysis by thinking about a simple rectangular cell with flow moving from left to right across the cell. And this cell has a length delta x, and the velocity approaching the cell is at a velocity u. And this is how we're going to set up the analysis. Now, over a time step delta t, we know that that flow approaching the cell moves a distance of u delta t across the cell. And in the diagram, you can see there that I've shaded that region in dark blue. So you can see that in our time step, the flow is going to move a distance of u delta t. And of course, the bigger the time step, the further that flow is going to move across the cell. Now, what the Courant number physically is, or the easiest way to remember it, is the Courant number is just the ratio of the two lengths which you can see there in the diagram. It's the ratio of the distance that the flow moves, u delta t, divided by the length of the cell delta x. So I like to think of the Courant number as the ratio of these two lengths, or alternatively, you can think of it as the fraction of the cell that a flow moves across it in a time step. So really, a Courant number is just a fraction of two lengths. And once you've understood this definition, it becomes easy to appreciate what the Courant number means when you actually look at it in a CFD solution. So if we consider two identical cells, then a Courant number of 0.3, what that's really telling us is that actually in a time step, the flow is moving 30% of the distance across the cell. Now, if we have a Courant number of 1.1, for example, which you see on the right, that means that the flow is actually moving all the way across the cell and then a further 10% of the length of the cell in a given time step. So really the Courant number is giving us a quick and easy way to look at cells and tell us how far across the cell is the fluid moving in a given time step. And of course, if the velocity changes, the time step changes, or the size of the cell changes, the Courant number will also change. But for all these cases, the Courant number is just going to be that fraction there. It's going to be for a given cell, how far across the cell is the flow moving in a given time step. Now, that 1D analysis is very straightforward and it's easy to appreciate, but the analysis gets a bit more challenging when we think about 3D cells with complex shapes that you might be used to seeing in your CFD calculations. And Furthermore, what happens if these cells are skewed? What if they're not perfect squares or perfect cubes? How would we define a current number then? Can we come up with a formula, a better way of calculating the current number? And can it account for complex cells with different shapes? So I've got for you some examples of cells which you may recognize from your CFD studies, tetrahedrons, pyramids, and even polyhedra. We need to have a definition of the current number that can account for cells with arbitrary shapes. And the definition that I'm going to go through now is the definition that is used by OpenFOAM and is probably used by the majority of other CFD codes, and is very general and can account for cells with different shapes. So for 3D cells, what we're going to do to motivate this is just think about what we need to do. We need some method of specifying the distance across the cell and the velocity u that's incident on the cell. Noting, of course, that the cell is going to have different size, shape, faces, and the shapes and the faces are going to have different orientations. So we need a method of specifying this that's consistent for all cells. But just to remind yourself what we're doing here, we need a method of specifying the velocity, that's the top of the fraction, and then the distance across the cell, delta x, as the bottom of the fraction. And the main trick that's used here by CFD codes to specify the current number for arbitrarily shaped cells is to write the distance as the cell volume divided by the total surface area of the cell. And of course, that fraction is dimensionally consistent. You've got a volume, which is meter cubes on the top of the fraction, and then a surface area, which is meter squared on the bottom of the fraction. So taking your arbitrarily shaped cell, taking its volume and dividing by its total surface area was one method of giving you the distance across the cell, delta x. And this is what the CFD codes do. And of course, we can go further and say that the total surface area is made up of the sum of the face areas that make up the cell. So what we would do for our given cell is take the volume and then add up the surface area of each of the individual faces that make up the cell, and that would give us a metric for the distance across the cell that we're going to use in the current number calculation. And of course, that's valid for any shaped and sized cell that we want. The next thing we need to do is we need to think about each of the faces that make up that cell individually. And what we need from these faces is we actually need the velocity normal to the face. And the way to think about this is if you look at the diagram on the left of the slide there, this is that same cell which we looked at the start of the talk, but of course now we're in 3D. And if we're in 3D, the velocity doesn't have to be normal to the face. You could have a face velocity that's at any angle or any direction. And what we need to think about is that, of course, in a time step, because the velocity is an angle to the face, the fluid is only going to move that shaded distance there, which you can see across on the slide. In a time step, it's only going to move that shaded distance. And so clearly what we need to do is we need to take the component of the velocity that's in the direction of the face to the cell centroid. And if we took that component and then multiplied it by the time step, that would give us the distance that the velocity has moved from the face towards the cell centroid. And because we're using vector calculus, the easy way to do that is to just take the dot product of the face velocity with the unit normal vector that's pointing towards the centroid of the cell. And that makes sense in 1D, but if you look at the image on the right of the slide, you can see that this definition also makes sense if you've got a more complex shape with multiple sides and some of the sides may be skewed. Clearly, in a time step, the flow is only going to move that shaded distance across the cell towards the cell centroid. So that's what we're going to do. We're going to use the velocity normal to the face from each of the faces that make up the cell in the definition of our current number. So now what we can do is go back to that original definition, and remember we want to know the distance that the fluid has traveled in a time step and divide that by the distance across the cell. So if we substitute for delta x and the velocity, we're now taking the velocity normal to the face, and of course we're going to have to sum over all the faces now, and that gives us the expression there which you can see in equation 5. And at a first glance, it might look like we've solved the problem. It might look like we've come up with a general method of specifying the current number for arbitrarily shaped cells. However, if we actually look a bit closer at equation 5, we can see that we have a problem here and we need to do something a bit better before we can specify the current number for arbitrarily shaped cells. So what is the problem? The problem is actually in that summation, we're actually summing the velocity normal to the face and the face area. And of course, this has the units of volume flux. And if we remember back from conservation of mass, then we remember that actually the total volume flux across all the faces of a cell will be 0. And that gives us a problem, because if we use the definition that we had in the previous slide, then we would just get a current number of 0, because the summation of that volume flux term will always be equal to 0. And so what we need to do is we need to do something a bit more clever so we can get around the volume flux summing to 0 if we want a definition for our current number. And the trick we're going to use is, rather than taking the velocity component that's normal to the face, we're going to take the magnitude of this term. And the reason we're going to take the magnitude can be understood if we actually just think about the cells and what's actually happening. So if we go back to our simple cell, which is at the top of the figure there, on the left face of the cell, we've got the velocity at an angle to the face. And then we've also got the velocity on the right face of the cell, which is also at an angle to the face. And if we were to sum up these contributions with the area, of course, the volume flux would be 0. But now, if we were to take the magnitude of this velocity that's normal to the face, in effect, what we're doing is reversing the flux on half of the faces. So if we now return to our diagram, we can see in the bottom diagram that actually the flux from the right face is now reversed effectively if we take the magnitude. And this will be a way that we can get around having the volume flux sum to 0 in our current number definition. But of course, there's one more thing we need to do, and that's because half of the volume flux contribution has been reversed, we also have to include a factor of a half. Otherwise, the volume flux will be twice as large as we need it to be. And this may not work out in your mind straight away, and so I've actually just come up with a really simple and easy way you can use to think about this, and this is the way I had to use to work it out. So if you think, let's just say that our face volume flux contribution from the left face was 4, for example, in equation 7, then we'd have -4 from one face and then +4 from the other face for the volume flux contribution, and of course that would sum to 0. But if we were to take the magnitude of these fluxes, you would have 4 and then +4, and that would give you a total volume flux of 8. But of course, we know that that's actually too large, and so if we include a factor of a half, that allows us to account for half of the face volume flux as being reversed. And so you can see we've gone from equation 7 there to equation 9, and that allows us to account for the sum of the volume fluxes being equal to 0. So now if we return back to our current number definition, we've actually got a complete definition for how we can specify the current number for arbitrarily shaped cells in 3D. And that's given by equation 10. We've got the current number is the summation of, this time, a half of that velocity component normal to the face, and we take the magnitude, and then that's multiplied, of course, by the time step, and then the face area divided by the volume of the cell. So remember, that's how we're going to get the distance across the cell. And what we're going to do from equation 10 to equation 11 there is just do a slight bit of rearranging. So bring the factor of a half and the time step out of the summation, and that allows us to arrive at equation 11. And equation 11 is actually identical to the equation and the definition that's used by OpenFOAM, and is probably the definition used by the majority of other CFD codes. But of course, it's difficult to actually find out what definition they use because we can't see the source code. But for now, what we've done is we've successfully come up with a definition of the current number for an arbitrarily shaped cell, and we can apply this in 1D, 2D, or 3D, regardless of the shape of the cell. So that puts us in a really good position. And we also have a good understanding for what the current number actually means. It's the ratio of those two distances, the distance that the fluid moves across the cell to the size of the cell. So what I want to move on and talk about now is actually talk about the current number in a bit more detail and reveal a few things which you may not have fully understood and will really help you to understand the current number when you apply it to your own CFD simulations. And the first point I want to make is actually the current number as a field. So if we think back to that previous definition that we used, remember that we're using the face velocity and the distance across the cell and the time step. And of course, every cell in the mesh is going to have a different velocity on the face. And it's also going to have a different size and a different shape. So what that means in practice is that every cell in the mesh has a different current number. There's not one single current number for your CFD calculation. The entire CFD mesh has a current number associated with it. And if you actually look in the post processor of most CFD codes, you can often plot the current number as a field. So just like any other variable, like the velocity field or the pressure field, you can actually plot the current number field as well. And what I've got for you here is just a plot of the current number field for the flow over a backward facing step. And what you can see, of course, is that the current number is very different. It varies in the flow field. And broadly speaking, the current number is going to be larger when we have large velocities and small cells. And so looking at that flow field there, you can see that the current number ranges from 0 up all the way to about 0.3, and 0.3 being the location of those largest velocities. And I encourage you for yourself, for your own CFD simulations, if you've never looked at the current number field before, just have a look at some of your simulations and have a look at what the current number field actually looks like for your CFD simulations. It will really help your understanding. So before we move on to look at stability and how the current number affects the time step in CFD calculations, what we need to appreciate is that CFD solvers will use the maximum current number for these stability calculations and for the time step adjustments that we're going to look at later. And so if we go back to this example of the backward facing step flow, which you can see there, clearly the maximum current number in the field there is 0.3. And so the CFD simulation in this scenario will use a value of 0.3 for the current number, even though the current number varies throughout the mesh. And that's what we're going to do over the next few slides, is look at how this maximum current number is used to evaluate the time step and various stability criteria for the flow field. So the first thing that I want to point out quickly is that because this talk is very limited in scope, I'm not going to focus on maximum current number recommendations, because these often vary for different types of flow simulations. And so I've just listed on the slide for you here a variety of different flow simulations, and what you'll see is that actually the recommendation for the maximum current number varies quite considerably, depending on if you're doing a large eddy simulation or turbo machinery with some kind of implicit time stepping scheme. But for now, the point I want to make out is that most often for transient simulations, it's recommended that the current number is kept below 1. Now, for you in your simulations, you should look up in your field what the recommended current number is for the analysis that you're carrying out and use those recommendations. But for the purpose of the talk, what we're going to assume is that most often the maximum current number should be kept below 1. But remember to check it out for your individual simulations. So what does that mean, really, is that if the maximum current number has to be kept below a certain value, what does that mean for the physics of the simulation and what we're setting up? Well, of course, the size of the cell is set by the mesh, and we've done that ahead of time, so we can't make any adjustments to the mesh at the moment. And the velocity, we won't know before we carry out the CFD simulation, so we can't really make any changes to the velocity field. So in practice, what happens is that the maximum current number restricts the size of the time step that we can apply in the CFD simulation. So if our time step was above 1, if our time step resulted in a current number that was above 1, we would have to reduce that time step to bring the current number below the limitation that we wanted. And there are a number of ways that we can do that, but that's generally the thing to appreciate with the current number, is that if our time step is too large, that results in the current number being too large for the given flow field that we've computed, and we often then have to go back and reduce the time step to satisfy this criteria. And I don't really want to go into any more detail than that, because of course it varies quite significantly depending on the flow scenario that you're modeling. But one thing I do want to quickly talk about is adjustable time stepping, so that you understand actually what the CFD code is doing when it spits out a current number and a time step each time and you're trying to work out what it's doing. So the first thing we need to think about is what happens in a conventional transient simulation when we choose a fixed time step. So you set up your CFD simulation and you choose a fixed time step of, say, 0.2 seconds. You choose your time step and then you set the CFD simulation running. And what happens? So the CFD solver will compute the velocity field and all the other flow fields. And then what it will do, now that it has the flow field computed, is it will calculate a current number field for all of the cells in the mesh. So if you remember back to that slide where we showed the contour plot, all of the cells in the mesh will have a current number based on that velocity field that we've just calculated. What the CFD code will then do is evaluate the maximum current number, which in our case was 0.3, and it will then report that on the screen so that you can see it in the output file somewhere. But at this stage, what we're doing is we're using a fixed time step, so the CFD code will then proceed to the next time step and calculate the new velocity field, going back to step 2. And of course, this will then require the CFD code to recompute the current number field, given there in equation 12, which again will be different for every cell in the mesh because the velocity field has just changed. And what will happen is the CFD code will continue to repeat this step, proceeding to the next time step, calculating the current number, and just reporting it back to the screen. So what you'll see is you'll see the current number printed on screen there, but no adjustments are being made at that point. If the current number is too large, your CFD code may diverge and you may get a divergent solution or a crash. However, it may still converge with a current number that's too high. And under those conditions, you would have to go back into the code and reduce the time step to move and do the simulation again. But you can see with a fixed time stepping approach, it's not really very intelligent and nothing difficult is really going on here. All that's happening is the CFD code is just calculating the current number field and reporting the maximum value to you so that you can do something with that if you want to. But is there something better we could use? What about if we would use some kind of automatic adjustable time stepping? So what would happen if we enabled an adjustable time stepping simulation? What we would do is we would set an initial guess for the time step. So when loading up your CFD code, you might say, I'd like the initial time step to be 0.2 seconds. And then what you do is you also tell the CFD code the limit for the maximum current number that you want to achieve. So for the examples which we showed there on the previous slide, that may be 1 or it may be lower. And then what we do is we jump into the CFD code and we press go. And what will happen is that, like before, the CFD code will compute the velocity field. And now that it has the velocity field, it can calculate the current number field for all of the cells in the mesh. And once again, it will evaluate the maximum current number for that field, which in our case was 0.3. But what will happen now with an adjustable time stepping routine is that, like before, the CFD code will report the maximum current number to you on the screen, but then it will evaluate and see, is the maximum current number that I'm calculating in the field greater than the value that the user has specified? So in our case, the current number in that field which you saw in the contour plot was 0.3, which was less than the maximum current number of 1. So that's fine. The CFD code would then just continue to the next iteration and nothing would happen. However, if the maximum current number in the field was too high and was greater than the limit we applied, then the CFD code would automatically reduce the time step to bring the current number down in the next iteration. And that's generally the process of adjustable time stepping and how the adjustable time stepping works in the CFD code. So, of course, the important question to ask is, how does one update the time step? Clearly, you need to bring it down so that you can reduce the current number, but how does one reduce the time step? Now, a very simple way of reducing the time step might be just to take the old time step and then multiply it by the ratio of the maximum current number that we're allowed divided by the maximum current number in the mesh. And that would very rapidly bring the time step down. And of course, this is quite a simple way of updating the time step. And for those of you who are well practiced in CFD and numerical methods, you'll notice straight away that this method, of course, is quite unstable and can quickly lead to oscillations. And the reason for that, of course, is that if our current number is much higher than the maximum, then we're going to drastically reduce the time step by using equation 14 there. I mean, try for yourself, plug in a limit of 1 for the current number, and then propose that the maximum current number was 2, what we would then be doing is reducing the time step by half, which is quite significant. And this can result in oscillations and sometimes even divergence in the flow field, which you can see there in the plot on the left-hand side on the slide. And so, of course, there are a number of ways of getting around this. We can either use relaxation when updating the time step, or we can put in a hard limit there on the greatest change in the time step that we're allowed. And of course, this will vary with CFD codes. Some CFD codes will use relaxation and others will use some kind of hard limit. But either way, the aim is to get the change in the time step to look like the plot which you can see there on the right there. So we'll make small changes in the time step so that gradually we can reduce that current number and bring it back down under the limit, which the maximum current number that the user specifies. So I've been through quite a lot in the talk today, but just to give a quick summary of what we've spoken about, a reminder that the current number physically represents the fraction of the cell that the fluid moves across in a given time step. So if the current number is 0.5 in the cell, that means that in a time step, the fluid has moved half of the way across the cell. And that will vary throughout the mesh because every cell has a different size and the velocity in every cell is different. So actually the current number is a field which you can plot in a post-processor if you look very carefully at the variables that are available to you. And what CFD codes will use is they'll use and report the maximum value of this current number field every time step. And that's the current number which you see, which is given out to the user in the output file of the CFD code. And what we can do with the maximum current number is we can use it to update the time step either manually, or we can adopt some kind of adjustable time stepping scheme to reduce the time step and to keep a limit on the maximum current number that we have for our CFD code. So that brings me to the end of the talk. Hopefully in today's talk you've learned something new about the current number, either how it's calculated or how the CFD codes actually use it when they're evaluating stability criteria and adjusting the time steps. So I hope you've enjoyed the talk today. Let me know how you found it. Leave a comment in the comment section below. And until next time, I look forward to hearing from you.